In this example, we're going to look at an open pipe where we're trying to figure out the lowest frequency produced by this certain pipe with a certain length, and we know that the temperature of air is 20 degrees Celsius. Since we know the temperature in the air, first thing I'm going to do is I'm going to figure out the velocity of our wave. Since we know the speed of sound is 331.5 degrees Celsius plus 0.6 times the temperature in Celsius, I can just plug in the actual temperature of the air to figure out what the speed of sound is going to be with this current temperature. So it's just going to be 331.5 degrees Celsius plus 0.6 times 20 degrees Celsius. And if I just figure that on my calculator, I get 343.5 meters per second. The next thing I'm going to do, and I like to do this with these open pipe, closed pipe, and the string problems, is to draw out a picture of what I'm looking at. So if I have a pipe, let's just say this is my pipe here. If I'm looking for the lowest frequency produced by this pipe, I know the length of the pipe is 12 centimeters, and I also know that I'm going to have an antinode at both ends, because that's what happens when you have an open pipe. So if I have an antinode on this end, antinode on this end, the lowest possible frequency I could have is just a single node in the middle with my antinodes at both ends. And then if I just draw this in, here's my standing wave. So I have two half loops, and so the two half loops is one full loop. So since I have one full loop, that means that I have 1/2 of a wavelength. Now, since I know that the length of this loop is 12 centimeters, that means I know that 12 centimeters is half of my wavelength, which means if I multiply both sides by 2, that gives me my wavelength, which is 24 centimeters, which I'm just going to convert to meters, 0.24 meters. So now I know the wavelength of my wave. So I know the velocity of the wave, I know the wavelength of the wave. So the last thing I need to do is figure out the frequency. I'm just going to use my wave velocity equation to do that. So I know that V equals the frequency times the wavelength. So if I just plug in what I have, 343.5 meters per second equals the frequency times the wavelength, and the wavelength is 0.24 meters, I can just divide both sides. So 343.5 divided by 0.24, I get 1,431.25 hertz. So if I actually created a tube that's 12 centimeters long, that's open on both ends, and if I had 20 degree Celsius air, I would actually produce a sound in there, a standing wave of 1,431.25 hertz. That's the answer.